So that very last example that we did in the previous video segment was doing the chain rule backwards just by sort of looking at it and recognizing where that function came from. But there's a more systematic way of doing this that we're going to learn now. It's called integration by substitution. So if we suppose that we want to find this, if you think back to that day when we proved the chain rule way back in week 6, we replaced the inside function by just a simpler letter. The simpler letter then was u. So suppose that we let u equal x squared here, so that this then is going to become cosine of u, so that it will look a little simpler. So then, what is the derivative of this? Du over dx is 2x. Or, because what have I got up here? I've got a 2x and I've got a dx. So what if I do something that seems completely illegal and outrageous? And I rewrite this as du equals 2x dx. Now, you should be very skeptical here, because we've been saying all semester that this symbol du dx is not a what? It is not a fraction. It is the derivative. It is not supposed to be treated like a fraction. But we're doing it anyway. Let's see if we get the right result. So then, this integral of 2x cosine of x squared dx, what does that equal in our new variable? Well, cosine of x squared just becomes cosine of u. And all of this stuff, 2x dx, that's exactly equal to du. And this is a really nice, clean, simple function to integrate, right? Do you know a function whose derivative is cosine of u? Definitely. Sine of u plus c. Now, it was our own crazy idea to introduce this letter u into this problem that didn't have any u's in it. So we should go back to the original, just like we did in the first several examples when we were doing the chain rule, right? When we were doing the chain rule, we would get an answer that had a u in it. We would replace the u by the original inside function. So then this is sine of x squared plus c. And is that the same thing that we got in the previous example? Yes, it is. Now, you should be very doubtful and dubious about this, whether this is sort of legal to do or not. So it is legal. It's one of the beauties of Leibniz notation that it lets us pretend that this is a fraction. And in the next video, we're going to explain how it is that this ends up giving us the right answer and why it's justified to do it that way. But before that, we have an applet for you to experiment with. In fact, it's this very same function. It's, I think, a really cool applet because you get to look at the graph of this function and as a definite integral, meaning computing an actual area, and then the graph of this function. And as you slide, as you change the upper limit of this, the upper limit of this will change according to the rule u equals x squared. And then you can put in your own function as well. And what I hope this applet will convince you of, graphically at least, or numerically, is that we do get the same answer whether we are looking at the area under this curve or the area under this curve with this particular substitution. So go ahead and experiment with that applet, and then we'll come back and we will talk more formally about this method of u substitution.